All right. Next, we're happy to have Girish tell us about Fourier growth of XOR-Fibers of communication protocols.
Yes, so I'll be talking about this topic, and this is based on joint work with Makarand, Avishai, and Kevin. So there are a lot of buzzwords in this title, so I'm going to start by defining these concepts. So first, let's look at Fourier growth. Given a Boolean function, the level L mass of the function is defined to be the sum of absolute values of level L Fourier coefficients. Fourier growth refers to the growth of the level L mass, and by Fourier growth bounds, we mean upper bounds on the level L mass. Intuitively speaking, functions with small Fourier growth cannot aggregate many weak signals in the input to have a considerable effect on the output. In contrast, the majority function is an example of a function with large Fourier growth. This is a function that can distinguish between inputs that are just slightly biased towards 1 versus slightly biased towards -1. So this is what Fourier growth tries to capture. It turns out that Fourier growth bounds have applications in many areas. So in the field of quantum versus classical separations, it turns out that Fourier growth is exactly the key distinguishing concept between quantum and classical. It turns out that quantum algorithms can compute functions that have large Fourier growth, but classical algorithms cannot. Fourier growth bounds have also been studied in the context of pseudorandom generators. So roughly, functions with small Fourier growth are easy to fool. The original motivation for studying Fourier growth bounds was actually in learning theory, where it was shown that functions with small total Fourier growth are easy to learn. These are the various motivations for studying Fourier growth bounds. And Fourier growth has been studied for a large number of models, which I've described in this slide. Two models that we will be interested in and we'll revisit in this talk are parity decision trees and decision trees. For this model, we have optimal Fourier growth bounds. Yes.
Just a clarification. So when you say you can capture weak signals, what do you mean?
So this is a very loose concept, but essentially you can, so your majority function can distinguish whether your inputs have bias 1 over square root n towards 1 or -1 over square root n. This is what I call a weak signal, and the majority can distinguish these weak signals.
What would be another example of a weak signal?
Yeah, so in the correlation problem, it turns out that the level 2 signals are like 1 over n square root n, 1 over n. And in order to detect the signal, you need to have large Fourier growth. Okay, so yeah, we're going to revisit this Fourier growth bound for decision trees and parity decision trees. In general, getting optimal Fourier growth bounds is a very challenging problem, even for the first few levels. It really requires understanding the structure of these functions. There are many open problems regarding Fourier growth, and the problem we're interested in is Fourier growth of XOR-Fibers. So now let me say what XOR-Fibers are. So given a communication protocol, you can define the XOR-Fiber as follows. You look at the average output of the protocol over all x comma y such that x XOR y equals z. Call this h of z. So h is the XOR-Fiber. So the picture is as follows. You can view the communication protocol as this matrix where you have Alice's inputs and Bob's inputs. You're looking at the diagonal of x comma y such that the XOR equals z, and you're taking the average of the protocol. This is what we call the XOR-Fiber of the protocol. So although this XOR-Fiber seems to be a name that hasn't appeared before in literature, this has been implicitly studied in many areas, especially the area of XOR lifting. So in the situation of XOR lifting, it's kind of the reverse of an XOR-Fiber. Here you have a Boolean function, and you're defining a communication problem where Alice and Bob want to compute this function on the XOR of their inputs. More formally, given a function h, you can define a communication problem where Alice gets x, Bob gets y, and they want to compute h of x XOR y. So this is the XOR lift of a Boolean function, and functions of communication problems of this form are called XOR problems, and they're very well studied in communication complexity. It's not too hard to see that this XOR lift and XOR-Fiber are kind of reverses of each other, in the sense that if you have a communication protocol that exactly computes the XOR lift of some function h, if you compute the XOR-Fiber of this protocol, it is exactly H. So this is what we mean by an XOR fiber. And our goal is to study the Fourier growth of XOR fibers. Let me start by describing the motivation for studying this Fourier growth of XOR fibers. And there are many motivations. So one motivation is with respect to lifting theorems for constant size gadgets. So it's widely open to get any lifting theorem where the gadget size is constant. And any such lifting theorem would imply Fourier growth bounds on XOR fibers. If you get the optimal lifting theorem, it would imply the optimal Fourier growth bound for XOR fibers. So in some sense, all constant size gadgets, you can embed the XOR gadget in them. So really, this follows as an implication of lifting theorems for constant size gadgets, which is a major open question. It turns out that there are some applications of Fourier growth bounds for XOR fibers in these three areas, which I'll now describe. So first, what is the connection with parity decision trees and standard decision trees? It turns out that decision trees are a special class of XOR fibers, in the sense that given any decision tree, you can produce a communication protocol of twice the cost, such that the XOR fiber of that protocol is exactly the decision tree. Therefore, parity decision trees and standard decision trees are a special type of XOR fibers. So if you want to understand Fourier growth of XOR fibers, we first need to understand Fourier growth of decision trees and parity decision trees. Although these models are very studied, interestingly, it was only recently that people understood the exact Fourier growth bounds on these models. We now have a good understanding on the Fourier growth of these two models. So this is one reason to study XOR fibers. There are generalization of these models. The second connection is to quantum versus classical separations in communication complexity. So for this, let me start by telling you the situation in query complexity. So in query complexity, there's this problem called the k-fold correlation problem. And this problem was used to separate quantum query complexity and classical query complexity. So in particular, it was shown that this problem has a quantum protocol with k over 2 queries, but every randomized protocol requires like n to the 1 minus 1 over k queries. It turns out that the key concept used to show this separation was Fourier growth bounds. So in particular, this work by Bansal and Sinha showed that any problem that solves k-fold correlation, any model that solves k-fold correlation must have large level k Fourier growth. We already saw in the previous slide that decision trees have small Fourier growth. As a result, it follows that decision trees, classical decision trees, cannot solve the k-fold correlation problem. This is also an optimal separation. In the sense, any quantum algorithm with these many queries can be classically simulated with these many queries. So this is an optimal separation in query complexity. Now we ask, what about communication complexity? So it turns out that you can lift this separation from the query complexity world to the communication complexity world using this inner product gadget. And that gives you a problem in communication with a small cost quantum protocol with k rounds. But every classical protocol requires communication into the 1 minus 1 over k. Now we ask, is this an optimal separation? Can you get a better separation? So we suspect that the separation is not optimal, and that's really because you're using the inner product gadget. The hope is that if you lift this problem, this correlation problem with the XOR gadget, you will get a similar separation quantitatively, but the quantum protocol will require only half as many rounds. So one example of this is if you look at the case k equals 2, this previous result only gives you a separation between two-way quantum protocols and classical protocols. And one can ask, can you get a separation between one-way quantum protocols and classical protocols with the same kind of quantitative gap? And the hope is that if you lift to the XOR gadget, you will get such a separation. Indeed, the XOR gadget is much simpler than inner product gadget. So if you look at correlation lifted with XOR, it has a quantum protocol with half the number of rounds. In particular, the two-fold correlation has a one-way quantum protocol. In fact, it has a quantum simultaneous protocol, which is even weaker than one-way quantum protocol. So the question is then, what about the lower bound? If you lift with XOR gadget, does the same kind of lower bound hold? And to do this, you really need to understand Fourier growth for XOR fibers. Okay. So the last motivation for this I'm going to talk about is the connection with the gap hamming problem. So this gap hamming problem is a famous problem in communication complexity. It has applications to streaming lower bounds and so on. So in this problem, Alice gets a vector x, Bob gets a vector y, and essentially they want to tell whether the inner product between x and y is at least square root n or minus square root n. The way I've phrased it as an XOR problem. Here they want to compute they want to see if the XOR of x and y has large Hamming weight or small Hamming weight, where this large and small differ by square root n. So by Hamming weight, you should really think of the plus ones as 0 and ones as minus ones. So this is the gap hamming problem, and this is a very well-studied problem, and there are a number of different proofs that this problem requires omega n randomized communication. And one way of looking at this lower bound is through coin theorems. So in yesterday's talk, we saw what coin theorems are, but let me just briefly recap them. So the coin problem studies what is the maximum advantage in distinguishing biased coins from unbiased coins. The coin theorem says that this maximum advantage is proportional to the level 1 Fourier growth. And it turns out that you can do this gap hamming problem as a coin theorem for the XOR fibers of communication protocols. So let me describe this a little more carefully. So the point is, if you have a communication protocol that computes the gap hamming, then the XOR fiber of this protocol can distinguish between biased coins and unbiased coins, where this bias is 1 over square root n. Let me call this XOR fiber H. So this implies that by the coin theorem, the level 1 growth of the XOR fiber must be large. So if you could show that the level of Fourier growth of the XOR fiber is bounded by something in terms of the communication complexity of the protocol, it would give you a lower bound on the communication complexity of the protocol. So this is the connection of XOR fibers to the gap hamming problem. So any questions about these applications?
But you already have a good bound on that.
Yeah, so we give a new proof of this. Yeah. Okay, so now I'm ready to state our main result. Okay, so the question here is, what can we say about the Fourier growth of XOR fibers? The conjecture is that the Fourier growth of XOR fibers behaves like the Fourier growth of decision trees, in the sense that the level L Fourier growth is at most square root d to the L, if your cost is d. This is still open. The best bound we had prior to our work is d to the L, as opposed to square root d to the L. And our work really tries to bridge this gap between d to the L and square root d to the L. So for our first result, we prove the optimal level 1 bound of square root d. Our second result is to improve the level 2 bound from d square to d to the 1.5. We conjecture that the correct answer is actually order d. So this is our main result. So as described before, this result has some applications. So the level 1 bound gives you a new proof of the omega n lower bound for the gap hamming problem. The level 2 bound improves the lower bound on the communication version of the twofold correlation problem from n to the 1/4 to n to the 1/3. The correct answer we suspect is square root n, and for that you would have to prove optimal level 2 Fourier growth bounds. Finally, it also gives you a new proof for the level 1 bound for decision trees and parity decision trees. So any questions about our results? So yeah.
Higher than level 2.
So we think we can save a square root d factor for higher levels, which so I think the main focus should be to improve the level 2 bound to the optimal thing, because even if you generalize it to higher levels, you'll just save a factor of square root d. Okay, so now I'd like to tell you something about the proof. There are some very nice ideas in this, and hopefully I'll be able to tell you some of them. Okay, so the proof roughly consists of 3 steps. So in the first step, I'm going to view this communication protocol and Fourier growth through a geometric lens. There's going to be some random geometric process, And we're going to write some martingale on this process such that the final value of this martingale captures the Fourier growth. This is going to be the first part. Now, what we want to do is bound the final value of this martingale, and we want to bound the expected square of the martingale to be more precise. So to do this, you need to bound the sum of squares of step sizes of this martingale. It turns out that this is hard to do for general protocols. So we're going to assume that the protocol satisfies some nice properties. And this nice property turns out to be some kind of spectral notion of almost k-wise independence. I'll talk about this in I'll talk about this later. And I'll also try to give you some ideas as to why this is the right notion that we care about when trying to prove Fourier growth. And finally, I'll try to justify this assumption that we make on the protocol. Why is it the case that you can assume communication protocols have this nice structure? And for this, I'll give a cleanup procedure to convert an arbitrary communication protocol into a protocol that satisfies these assumptions. Furthermore, this communication protocol is not too much bigger. This is the broad outline. And at a very high level, this is very similar to how the Fourier growth for parity decision trees and decision tree works. There, you don't need to use some spectral notion of k-wise independence. You can actually impose perfect k-wise independence. And this is because decision trees and parity decision trees are highly structured objects. But for communication protocols, this is much harder to do. So in particular, if you look at the sets that Alice and Bob have, in the middle of the protocol, these sets could be arbitrary subsets of the Boolean hypercube. It's going to be impossible to enforce these sets to be k-wise independent, perfectly k-wise independent. So we can only impose some approximate notion of k-wise independence, and a priori, it's not even clear what this approximate notion of k-wise independence should look like. So that is one of the key contributions of this step, which is what kind of k-wise independence we use and why it's useful. And it turns out that this cleanup process is also highly non-trivial. In fact, this is the most technically involved part of our work, where we show that you can clean up this protocol using very few steps. So yeah, so this is the rough outline. Now let me get into the details of the proof. So let's start with step 1. For now, I'm just going to work with level 1. So first, go ahead.
So yeah, I think I'm confused about the definition of XOR-fiber. So what is so it's a function from what is the domain and what is the range?
Okay, I think it'll help to probably write down this definition and keep it throughout the talk. Maybe that. So you have a communication protocol where Alice's and Bob's inputs are +1 - 1 to the n. And the XOR-fiber H is +-1 to the n to -1, 1, where h of z is the expectation of, see this? Okay.
Communication protocol is just a function. It's not the transcript.
Yes. So here I'm identifying the communication protocol with its output. I'm thinking of CFXY as the output. So as a picture, it's just this. Look at the fiber corresponding to Z, which is all the points XY such that X XOR Y is Z. And you take the average of the protocol over this fiber. You do this for every fiber and call that function H. Any other questions? So let me start by describing the first step. So here I'm going to rephrase this problem using a geometric perspective. I'm going to write down some martingale that captures the level 1 Fourier growth. So first, how do we think of a communication protocol? We think of it as a tree. So here I'm going to make a lot of simplifying assumptions. So Alice and Bob are going to just send 1 bit at a time, and they're going to keep exchanging, they're going to keep taking turns. So here is an example of such a communication protocol where Alice starts by revealing the value of her first coordinate, then Bob reveals his first coordinate, and so on. Based on the actual inputs they receive, they might go left or right. So here is an example of this input, and here is the path that you would follow on this input. Finally, at the leaf, you have values 1 or -1, and when the players reach a leaf, they just announce this as the answer. So this is how we think of a communication protocol. And this is a very special type of communication protocol where the information that Alice and Bob sent is just the coordinates of their input. So this corresponds to a decision tree-like protocol. In general, communication protocols can be much more complicated. So at each point, Alice can reveal f of x, where f is an arbitrary function of x. Similarly, Bob can reveal an arbitrary function of his input. So this is the structure of general communication protocols. Throughout this talk, there'll be an underlying distribution on the inputs of Alice and Bob, and this is just the uniform distribution. We're always going to sample the inputs of Alice and Bob, x and y, independently and uniformly. And this is what introduces the randomness into the process. This induces a random walk on this tree. We're going to define some martingale based on this random walk. Okay, so now I'm going to give the geometric picture. And the point is that you can view a communication protocol as a partitioning process of the input space. At the start, you have the space of all possible inputs, which is plus 1 minus 2 to the n times plus 1 minus 1 to the n. And as you go down this tree, this induces a partitioning process for the space of all inputs. So in more detail, if you are at some node, and let's say Alice is speaking, so first of all, at any node, the set of inputs that reach this node is going to be a rectangle of the form A times B, where A is a subset of Alice's inputs and B is a subset of Bob's inputs. When Alice speaks, she's announcing f of x. And what this does is partition her set into two parts, those for which f of x is 1, those for which f of x is minus 1. So when Alice speaks, she's partitioning her set into two parts. And when Bob speaks, he's partitioning his set into two parts. So as you go down this tree, you can think of this process where one of the players' set is being partitioned into two parts. And because the inputs are sampled uniformly at random, each player is picking one of the parts at random with probability proportional to the measure of the part. There's also this random walk that's going on. And it turns out that the level 1 Fourier growth is captured by the inner product between Alice's center and Bob's center. So let me describe that in more detail. So given Alice's and Bob's sets, you can keep track of the center of the set. So the center is a geometric concept, and you can think of, it has many different names: centroid, center of mass, all these things. They're all the same thing, and they're defined by this equation. You sample a random point in the set and look at the expected value of that point. This is an n-dimensional vector, and it captures the center of the set. We're going to keep track of Alice's center and Bob's center as you go down this protocol. First, you can see that these centers, U and V, are vector-valued martingales, in the sense that if you take a set and you divide it into two parts, if you look at the average of the two centers, you're going to get back the original center. So these centers are themselves martingales. We're going to look at the inner product between the two centers. It turns out that this is also a martingale. And the reason is because when Alice speaks, she is modifying her center, but Bob's center stays the same. So only this part changes. And when Bob speaks, only his center changes. Alice's center does not change. So as a result, the inner product between Alice's center and Bob's center is also a martingale. In particular, if you look at the final value of the martingale, it gives you a bound on the level 1 Fourier growth. If you look at the expected modulus of this martingale at the end, this is a bound on the level 1 Fourier growth. So I will justify this in the next slide, but are there any questions about the setup? Sorry? For any protocol, yeah.
It's the same question, but it looks like you're only dealing with deterministic protocols. Don't you want to?
That's a good question. So I swept this under the rug. Indeed, but the point is that level 1 Fourier growth is kind of, it has this property that it's convex, in the sense that if you take an average of communication protocols, the level 1 Fourier growth is bounded by the average of the level 1 Fourier growth. So it suffices to work with deterministic protocols. Yes. Okay. So let me justify this connection between the level 1 Fourier growth of the XOR-fiber and this inner product between the centers. So essentially, the idea is to just focus on rectangles. Since any protocol can be broken up into rectangles, let's just see the connection between the Fourier growth of the XOR fiber of a rectangle and this quantity. So the basic idea is the following three facts. So the first fact is if you take a rectangle A times B and you compute the XOR fiber of the rectangle. So here when I say XOR fiber of a rectangle, I just mean think of these as the indicator functions of Alice's and Bob's sets up to some normalization. If you compute the XOR fiber of a rectangle, it's precisely the convolution of A and B. This just follows from the definition of an XOR fiber. So for a rectangle A times B, the convolution, the XOR fiber is just A star B. And the second fact is that the Fourier coefficients of the convolution are products of Fourier coefficients. This is a very simple fact in Fourier analysis. Finally, this vector here, the level 1 Fourier, so if you take a set and write down the level 1 Fourier coefficients as a vector, this is exactly capturing the center of the set. This is also something that's a very simple fact. You can write down the Fourier coefficients, and the level 1 coefficients are captured by the center of the set. So together, these three facts imply that if you look at the XOR fiber of a rectangle A times B, and you just add up all the level 1 Fourier coefficients, you get this inner product between the center of the Alice's set and the center of Bob's set. There's some cheating I've done here, which is ignore the signs on the level 1 Fourier growth, but this can be done. Okay. So this is just the way to view the level 1 Fourier growth as this geometric concept. So now I'm going to restate the whole problem completely geometrically. So even if you missed out the Fourier growth and XOR fibers, now is a good time to jump back in. Okay. So here is the main problem that we're studying. We have this random geometric process of partitioning the input space. So first, Alice partitions her set into two parts, and she chooses a random part with probability proportional to the measure of that part. Based on this, Bob partitions his set into two parts and chooses one part at random with probability proportional to the measure. Then Alice does this again, and Bob does this again. And at each step, we keep track of the centers of the resulting sets. This partitioning process is adaptive in the sense that the way the players partition their set can depend on the history up to this point. And what we want to do, so they do this D times. And what we want to show is that the final center of Alice's set and Bob's sets are not too correlated. More precisely, we're looking at the inner product between Alice's center and Bob's center. In the end, we want to show that the expected modulus of that is small. It's at most square root B. So this is just a restatement of the level 1 Fourier growth bound in this picture. Yeah. So looking ahead, it will turn out that each of these vectors is roughly square root D bits long. So this inner product could potentially be as large as D. But what we want to say that is that typically it's at most square root D. So let me describe this in the next slide. You can show that this martingale that we care about can be bounded by order D in the worst case. That is, for every leaf of this protocol, this martingale is at most order D. And the justification of it is the following. So you can just bound this by Cauchy-Schwarz by the product of the norms. And the point is each of these quantities is going to be at most square root D by an application of the level 1 inequality. So what does the level 1 inequality say? It says that if you are given a set in the Boolean hypercube that is not too small, then its center cannot be too far from the origin. In particular, if you have a set of measure 2 to the minus D, its center is at most square root D away from the origin. And because U and V are the center of Alice's and Bob's sets, and in a protocol, you can kind of assume that Alice's and Bob's sets at the leaf have measure at least 2 to the minus D, it follows that each of these centers is at most square root D long. And this gives you the order D bound. What we really want to show is that typically it's at most square root D. So we will show that the expected square of this final martingale is at most order D. This would imply by Cauchy-Schwarz the bound that we want.
So is this optimal for partitions if I don't consider protocols, but just partitioning?
Exactly, exactly. So we're really using the fact that there's a martingale going on, which doesn't happen if you just have an arbitrary partition.
What do you think the answer is to partition?
Oh, that's a good question. I think that the first bound is tight because there's no kind of martingale cancellation behavior going on, but I don't know. Okay. So what's happening here is that these vectors u and v can be square root d bits long, but on average, they're going to be close to orthogonal. That's what we're going to show. Let's see an example of this to make things concrete. So let's look at a simple communication protocol where Alice and Bob are simply revealing the first b coordinates. This effectively partitions the input space into subcubes. If you look at the leftmost path, then Alice and Bob are setting their first d coordinates to be 1. In this case, the resulting sets are basically all points whose first d coordinates are 1. The centers of such sets is basically this point where the first d coordinates are 1 and the rest are 0. Now, if you compute the inner product between these two centers, it's going to be d. So this is saying that the first bound we derived is tight for a worst case leaf. But the point is when you take a random leaf, you're going to get cancellations. So when you take a random leaf, the values you set to Alice's coordinates and Bob's coordinates are going to be independent because these inputs were sampled independently. And as a result, you're going to set the first d coordinates of Alice to be A and Bob to be B. So when you compute the inner product between the centers, you're going to get the inner product between A and B, which is typically square root d. So this really highlights the phenomenon of cancellations that occur when you take a random path. The intuition is that when you sample X and Y independently, the resulting U and V, the centers of Alice's and Bob's set, should be kind of independent in the sense they should be kind of orthogonal. This is not true because the centers can be highly correlated as a result of the communication protocol. Nevertheless, we want to say that typically they're roughly orthogonal. This is the kind of statement that we want to prove, regardless of what kind of communication the players send and no matter how they partition the protocol. So this is the problem. Any questions at this point?
Yeah, I mean, like everything you did was completely general except for the, I guess the part you're gonna do that's which is like you need to show that every step the square is smaller, like the sum of the squares. The martingale, the quadratic variation of the martingale is bounded.
Yes, but this turns out to be surprisingly hard. So I think, so we'll see what the calculation for the step size is and we can see why it's so hard to bound the step size at each point. So hopefully I'll be able to answer your question. Yes.
So again, on the product of these centers.
Yes. So the inner product of these centers is exactly capturing the level 1 Fourier growth of the XOR fiber. So this is the claim that I didn't fully prove, but the point is that if you look at the inner products at the leaf, and you take the expected modulus of this inner product, it's a bound on the level 1 Fourier growth of the XOR fiber.
Is there intuition?
Yeah, so the intuition I kind of rushed over, which is that it's actually a really simple calculation, but so I kind of hinted at this calculation for rectangles, but we can go over it again. So here, if you just look at the particular rectangle in the protocol and you compute the XOR fiber, the XOR fiber is just going to be the convolution of the two sides. And if you take the Fourier coefficient of the convolution, it's going to be the product of Fourier coefficients. So these are the Fourier coefficients, and now you're adding all the level 1 Fourier coefficients. So you get summation A hat I B hat I for all I. And this is A hat I is just captured by the center of A. So it's just taking the inner product between the center of A and the center of B.
So if you're looking at like level 2, it would be the covariance.
Exactly. So it would be the expectation of X tensor X. Yeah. So, okay, so now let me move on to step 2, which is how do we bound the sum of squares of step sizes? And this turns out to be a hard problem, and we need to make some assumptions on the protocol. Namely, we are going to define some spectral notion of two-wise independence and show that under this assumption, you can bound the sum of squares of step sizes. So let's see what this is. So first, let me try to tell you ahead what we're going to do. So you have this martingale, this inner product between Alice's center and Bob's center. We want to show that the sum of squares of step sizes of this martingale is small. So let's compute the step sizes. So at time I, if Alice is speaking, only her center is going to change. And let's call the change in her center as ui plus 1. The change in the martingale is going to be this inner product. Now, if Bob is speaking, only his center is going to change, and we're going to call vi plus 1 the change in his center, and the change in the martingale is going to be this inner product. And we really want to bound the sum of squares of step sizes. So let's see what bound we can prove. So assume that each step, this change in the center of mass is just a unit vector. This is a simplifying assumption, but it's not so important. So at each point, Alice and Bob are just adding a unit vector to their center of mass. In this case, if you apply Cauchy-Schwarz, you just get a bound of step sizes at most the norm of Alice's center and the norm of Bob's center. So this is just Cauchy-Schwarz, but this is not good enough. So we already showed that each of these things is at most square root I by the level 1 inequality, and this is also tight. So the example we saw before actually shows that this bound is tight. So then what happens is that each step size can be as bad as square root I. So when you add the square of step sizes from 1 to d, you get d square. So even to bound the step sizes, assuming these nice assumptions, it's not clear how to do it. And this is the key step. We're going to show that if Alice's and Bob's sets satisfy this nice spectral two-wise independence property, then you can bound the step size by the change in Bob's center and by the change in Alice's center in the previous round. This might look a little counterintuitive. We're looking at the step size at time I. We're going to bound this by the change in Bob's center in the previous round. And similarly, we're going to bound this by the change in Alice's center in the previous round. So this is what we're going to do. And if you can do this, then we're in good shape. Basically, if you add this up over all I, it's going to be at most order d. So now let me define what the spectral two-wise independence is. We say that a set S is elongated in direction V if the variance of that set in that direction is large. So you look at the projection of the set on this direction V, which is this random variable x dot p, where x is uniformly random from S. If this random variable has large variance, we say that a set is elongated in this direction. Pictorially, it's just this thing. You have this set which is elongated in this direction, and you have this set which is not elongated in any direction. So this is what this is trying to capture. We say that a set S is spectrally two-wise independent if it is not elongated in any direction. There's another way to say this, which is look at the covariance matrix of a random point sampled from S. This covariance matrix must have small spectral norm. So this is what we mean by spectrally two-wise independent. And it turns out that if you can ensure that Alice's and Bob's sets are spectrally independent throughout the protocol, then you can derive a bound on the martingale step sizes. So now I'll try to justify why this is the case. Why is this a property we should care about? So any questions about the definition of spectral independence? So why is this concept so useful? Okay, so here I'm going to introduce an imaginary communication step. Just imagine that Alice is going to reveal the inner product of her input with Bob's center. So she's going to send Bob the inner product of X with V, where V is Bob's current center. We call this the Gram-Schmidt step. So I'm doing some cheating here. This is a real number. So what does it mean to send this real number? There are two ways of handling it. So one, you can round this real number to some precision and send the finite version of this. But it turns out that this introduces some errors and you won't get the optimal level 1 bound, you'll get some log n factors. So in order to get the precise bound, we really need to let Alice send a real number to Bob. But this forces the inputs also to be real. Because if X was Boolean, revealing X dot V could end up revealing X. So we really need to allow the inputs X also to be real. And that's why for the level 1 bound, we allow protocols with real inputs and real communication. And this is what gives us the optimal level 1 bound. But I'm not going to get into this. And for this talk, you can just keep either picture in mind. Okay, so what is this step doing? Alice has a set A. She's looking at this direction and she's slicing her set into slices along this direction. So that's what this step is doing. Why is this such an interesting step? So it will turn out that the change in the martingale as a result of this step is precisely equal to how elongated Alice's set is in the direction V. So this Gram-Schmidt step is what connects the change in the martingale to the elongatedness of the set. So that's the power of this Gram-Schmidt step. So let's see why this is true. It's not too hard to see. So what is the change in the martingale? So this is the expected change in the martingale as a result of this step. So what is this quantity? So this is the value of the martingale at time I+1. This is the value of the martingale at time I, and we're computing the difference between the expected squares. So this is the step size square. And now I'm just going to replace the center by the definition of the center. So this U is basically the expectation of a random point sampled from Alice. So here I'm just replacing U by its definition and replacing U here by its definition. And the key point here is that for every point within this slice, it has the same inner product with V. So for every point X dot V here, when you take X within the same slice, it's actually the same. So here this expectation is actually over a constant. So you can pull the square from outside to inside, and you just get the expected square of this inner product. And now this quantity, by definition, is the variance of Alice's set in the direction V. So the details here are not so important. The point is that this Gram-Schmidt step expresses the change in the martingale in terms of the elongatedness of the set in direction V. So this almost gives us what we want. So what do we actually have to do? We're actually going to introduce this Gram-Schmidt step at every node in the protocol. So you take the original protocol. Whenever Alice is supposed to say something, we're going to first tell her to do this Gram-Schmidt step and then do whatever she was supposed to do. The advantage of doing this is, first, you can express the change in the martingale during this step as a measure of how elongated Alice's set is in this direction V at most I, and this direction is Bob's current center. And what's interesting is that we did this Gram-Schmidt step before, as a result of which the variance of Alice's set in this direction equals the variance of Alice's set in this direction, where Vi is the change in Bob's center. So why is this the case? The point is here, Alice has revealed the inner product with Bob's old center. So by the time you reach here, the inner product with Bob's old center is already fixed. That means the variance of this set along that old center is 0. So when you compute the variance along this direction, you might as well subtract Bob's old center because the variance along that direction is 0. So as a result, the variance along this direction equals the variance along the change in Bob's center. Yes.
How do you measure the size of the rectangle snap? That's down. There might be a single point X. And that's my inner product.
So in the reals, usually that won't happen. You'll have slices. So you can talk about relative measure. So we do have to talk about like relative measure within the subspace. Oh, just the just the Gaussian measure on the subspace. So if you have the Gaussian measure on the full space and you look at a subspace, it induces a Gaussian measure on one less dimension, and you look at that measure, this measure of the set under that Gaussian. Does that answer your question?
So you're measuring the intersection of the rectangle with the Gaussian?
With the subspace, yes. Using the Gaussian measure on the subspace. Yes. Okay. So now the point is that we've expressed the variance in this direction in terms of the variance in the change in Bob's center, and now we're in good shape. This is what we wanted. We wanted to say that if Alice is, so because Alice's set is two-wise independent, the variance in this direction is at most the norm square of this direction. And this is the change in Bob's previous center. Okay, so the point of this step is that you can bound the change in the martingale in this step using two-wise independence. And it turns out that this Gram-Schmidt step has this nice property that the other steps don't contribute anything to the martingale. And this is really why we call this the Gram-Schmidt step. The point is, at this stage, Alice has revealed the inner product with Bob's center. So any further change in her center is going to be orthogonal to Bob's center. So the martingale here is going to not change at all. Okay, so let me summarize what happened here. We introduced this nice property called two-wise independence, which means that a set is not elongated in any direction. We introduced this Gram-Schmidt step, which connects the change in the martingale with the elongatedness of a set. We said that if a set is not elongated, then you can control the jumps in this martingale. So the whole problem becomes, how do you ensure that these sets are not elongated in any direction? So now I'm going to move on to the third part, which is how do you ensure that the sets are not elongated in any direction? So any questions about step 2? Okay. So now this is kind of an independent question on its own. So even if you didn't follow step 2, step 3 can make sense on its own. So here the problem is you have a set that is not clean. It's elongated in many directions. How do you partition the set so that it's not elongated in any direction? There's a very natural cleanup process. Every time you have a set like this, which is elongated in this direction, you simply slice it up along that direction. This is again kind of like a Gram-Schmidt step, but the vector you choose is the direction along which your set is elongated. And the advantage of doing this is that within each slice, the variance in direction V is 0. So now the question becomes, how many times do you have to do this process? So this is the main technical lemma in our paper. We show that for a communication protocol of cost D, you can clean it up using typically ordered D steps. So all of Alice's and Bob's rectangles can be cleaned up using just a constant blow up in the communication cost. This is our main lemma. Let me tell you a special case of this main lemma, which was actually proved in a work by Thomas Vedic. So this says that if you have a set that's not too small, then it cannot be elongated in too many directions. In particular, if your measure of the set is 2 to the minus d, then there can be at most order d orthonormal directions along which your set is elongated. This can be proved using some kind of a structure versus pseudorandomness argument or some density increment argument. The point is that every time your set is elongated in some direction, that direction gives you at least one bit of information about that set. So when you slice up the set along the direction and you take a random slice, the relative density of the set goes up. It at least doubles at each step. And since the original measure of the set is 2 to the minus d, you cannot do this doubling more than d times. So that's the idea behind this lemma. The general case is significantly more complicated, and let me try to tell you why. So first, we need to clean up every internal node of this protocol. It doesn't just suffice to clean up the leaves. So what happens is that this partitioning and cleaning process occur in an interleaved fashion. So first Alice is going to partition her set, then you're going to clean it up. Then again, Alice is going to partition her set, clean it up, and so on. So we really need an adaptive version of this cleanup process. Secondly, cleaning a set might produce new bidirections. So here is an example of a set that is only elongated in this direction. Assume that the measure of this slice is small. But when you slice it up and you take this slice, it's going to be elongated in this direction. So our cleanup process really needs to handle all this. And that's what makes this more technical. And nevertheless, we're able to do this. So this is what I wanted to say about the cleanup process. Finally, let me tell you about the level 2 bound. So as Nikhil said, you can do some similar things where you look at the level 2 center. So you look at expectation of x tensor x, and all this martingale behavior turns out to be true. But the hard step is this cleaning process. So let me tell you what we need to clean and how much we're able to clean it. So what happens for level L equals 2? So the notion of clean turns out to be this. We say that a set S is elongated along a bilinear form. If you look at this random variable in a product between x tensor x and v, this is some bilinear form. If the variance of this quantity is large, we say that a set is elongated in this bilinear form. We say that a set is spectrally 4-wise independent if it is not elongated in any bilinear form. So any perfectly 4-wise independent set is also spectrally 4-wise independent. And this is the property that we want Alice's and Bob's sets to satisfy. And here is what we need to do. Given any set that is not too small, we want to show that you can partition it into a few parts such that a typical part is spectrally 4-wise independent. So if the measure is 2 to the minus d, you want to partition it into 2 to the d parts such that each part is spectrally 4-wise independent. Of course, we will eventually need an adaptive version of this and so on, but this is the main question. And the difficulty is in some sense that this baby lemma is no longer true. You can have sets whose measure is like 2 to the minus d, but there are d square bilinear forms along which the set is elongated. And really, this is the example. But the key point here is that even though there are so many bilinear forms, there are actually these d pieces of information that once you fix these d pieces of information, it kills off all these d square bilinear forms. So that's the hope. And maybe there is some other way of partitioning so that you can still do this. So let me tell you a little bit about what we do to get this d to the 3 halves bound. Essentially, we modify this definition of cleanliness to be 10 times d. And then it turns out that there are at most d bilinear forms along which your set is elongated. So our notion of clean is d times bigger than what it should be. And this essentially gives us a d times the correct sum of squares of step sizes. So, so let me end my talk here. I'm happy to take questions now.
So repeat a question because so what can you say about partitions in rectangles?
Yeah, I don't know. I would expect that there's no kind of martingale process going on. So I would think that order D is the right answer. I don't have an example in mind, but I would think that you can't improve on this.
So that question should be like pretty equivalent to asking like about the partition number of the gap Hamming problem, right?
So I think the gap Hamming lower bound is actually proved using some kind of partition bound. They say that fix any rectangle of measure 2 to the minus d, then you get some contradiction. Such an argument necessarily doesn't use anything more than the fact that you have a small partition. So I think the gap Hamming lower bound actually, you get some kind of partition bound. So that the number of partitions should be less to the n. So I'm not sure. Yeah.
So it seems your kind of bound cannot be proved for a single rectangle, only for partitions, but it potentially could be proved for partition with rectangle. I mean, not this
yes,
proof,
it could
but
be.
maybe some other.
It could be, yeah. I mean, it's possible. Maybe there are still cancellations. I don't see why. Yeah, I don't know.
Any more questions? Okay, if not, let's thank Uma again.